Hello, everyone. Hope you are well. Let's start our lecture, continue our lecture on Introduction to Simulation. So we're going to do the fourth part of the Introduction to Simulation, which is chapter 10, and then we're gonna be done with chapter 10, and we're gonna move on to chapter 11. So let's get started with chapter 10 and finish it. So this is the fourth part of Introduction to Simulation. We're gonna see more interesting examples here. We're going to start off with inventory management, if you're familiar with it. So inventory management is when, as a manager of inventory, you would want to see, you want to actually minimize the cost of inventory. So one cost of inventory is you don't really want to keep a lot of inventory because that's going to cost you the maintenance, the spoilage, but also there's going to be a cost of opportunity if you don't have enough in a stock to meet the demand in the market. But the demand is going to be random. Daily demand is going to be random. So that's why we do a simulation here to address these uncertainty. The other point here that is important is when should you actually restock your inventory? Because, you know, for example, if you have just filled out your inventory last week, you're going to have daily demand. So your inventory level is just going to drop. And if you don't restock it, it's just going to go to zero. But that's not how they handle it. In reality, there's going to be a reorder point. That means that there is like a certain number. If the level of inventory just falls below that, they're going to order. That's going to be the order point. So for example, whatever number it is, say 50, 60,000, depends on your system. And it's going to take a time when you order something for your inventory until you receive it. Say 1 day, 2 days, or a couple of weeks if it comes from a foreign country via ship, for example, via oceans. So that's going to be called lead time. The time that it takes when you order, since you order until you receive your order. So that's called lead time. And during the lead time that you have ordered whatever you want to restock your inventory, you still have demands to meet in the market. So you have a possibility of what is called that stocking out. That means that because the daily demand also fluctuates, it's random, uncertain. So this is what we want to do here. We want to compute the reorder point in such a way that we have a certain level of service level. Service level is the opposite of a stock out. So that's 1 minus the probability of a stock out. So we have two sources of uncertainty here. We have the daily demand, which we assume in this example that follows a normal distribution with an average of 25 and a standard deviation of 5. And we also have for the lead time, that's going to be also random. So we assume that here it follows a made up discrete distribution. So the lead time can take 1, 2, or 3 days with a probability of 30%, 45%, and 25%. So the question is, what should the reorder point be so that the company would have a 90% service level or 10% chance of stocking out? To solve this problem, we're gonna first build up the influence chart for that. So we're gonna start with the output. The output is the service level. So the service level is the output. We're gonna start from the end. And then we see what influenced the service level. The service level is going to be influenced by the number of applications that we do, because it's going to be a simulation. So we need to do a lot of application here, say 1,000, a couple of hundred. And the other one is the stock out, or the probability of a stock out for each, whether we have a stock out or not in each replication. And then for the general simulation, we find the probability of a stock out, and that's going to give us the service level. For the stock out, you would have the stock out would depend on the reorder point, how many are left in the inventory when you start your order, or what is the trigger point for the reorder point. And the total lead time demand, that means okay, how many days it's gonna take since you order until you receive your order. And the total lead time demand depends on the daily demand, which is also a random variable, and also the lead time base, which is also a random variable. The daily demand in this our example actually follow the normal distribution. So we know the mean and sigma distribution. These are going to be our input. So that's why it's input. It has a blue color. Service level again is 1 minus the probability of a stackout. So it's going to be 1 minus when you run the experiments multiple times. It's going to be 1 minus the number of stackouts that you have in several replications divided by the total number of replications. So that's when I give you a service level. So this is how we're going to model this problem in Excel. We're going to use VLOOKUP function for the sampling from for lead time random variable based on the discrete random variable that we have. We had done actually similar example before for this sampling from a random probability distribution. For the to sample from the demand, which follows a normal distribution, we can use the norm.inv, norm inverse. And then we're going to give it the rand function, which is going to generate the random number between 0 and 1. And then we're going to give it the other two parameters, which are the average and the standard deviation for the daily demand. For day 2, we're going to actually use an if function, if statement, and we say that, okay, if the lead time is greater than 1, then generate a sample from the normal distribution. So, and if not, then just leave it out or leave out a 0 or just leave out an empty space. Okay, so this is going to, for day 2, we're only going to generate or sample from the normal distribution for the daily demand, if the lead time is greater than 1. If the lead time is just 1, we don't have daily demand because we don't have day 2. Okay, we don't have day 3. For day 3, the same. So we're going to say use an if statement, say that, okay, if the lead time is greater than 2, that means that, okay, if day 3 it exists for the lead time, then generate or sample from normal distribution for daily demand. If not, then you can print out a 0 here, output a 0 here, or you can just leave it an empty space to make our sheet a little more neat and clean. Then we're going to have to compute the total daily demand for the lead time. So total lead time demand. And that's going to be the day 1 demand, day 2 demand, and day 3. So we're going to sum all these 3 up. After we have computed the total lead time demand, we can compute the ending inventory level to see whether we have a stockout or not. So, and that's going to be the reorder point, which is going to be decision variable, minus the total LTD that we computed here, which is going to be a random value. So if this is value, if the ending inventory value is negative value, then we're going to print out the 1 here. That means that we have a stockout. Otherwise, we don't have a stockout. And then we're going to replicate these values and computation several times for several applications, for example, 1000, and then we compute the service level. And then we're going to build up 95% confidence interval for our system. Okay. All right, so let's open up the Excel files. So I have opened the reorder point data file. Let me share the video. All right, so you see here some inputs. We have the daily demand random distribution, which is normal distribution, average of 25 and a standard deviation of 25. I'm going to first name these values, range names. So this is mean. So this is the standard deviation. And then here we have the lead time distribution. So we have for day 1, the lead time can be 1 day. With the probability of 30%, it can be 2 days with probability of 45% and 3 days by probability of 25%. So here I'm going to generate the cumulative kind of probability, so I can use the VLOOKUP function. So we're going to start up with 0 always. And for the next row, it's going to be this probability plus the previous probability in the same column. I can drag this down now. So this is going to be my cumulative probability distribution for the lead time. So I'm going to call this the lead time lookup. Okay. So if you use the name range, you see that we have LT lookup, the mean, the standard deviation. The decision variables is the reorder point, as you remember from our lecture. So here I'm going to use my decision formatting here. I'm going to give it a value, say 50, just to have a value here. Okay. And I'm going to name this as well. All right. And in this columns and cells, we're going to do the experiments, the simulation. So the first column just shows the cycle number or the simulation replications. I'm going to start off with the first replication. The lead time here, I'm going to generate or sample from the lead time distribution. So I'm going to use the VLOOKUP function, and then I'm going to generate the random value using the rand function. And then I'm going to give it this table, the LT lookup, and I'm going to ask it to give us the random days here corresponding to the random probability that it has here. So for example, here is 1. If I refresh it here, you can see that it's going to generate different numbers. So these are for the daily demand lead time. For day 1, we're just going to sample from the normal distribution. So it's going to be norm.ind. And I'm going to generate a random number using rand function. And then I'm going to give it the average of the normal distribution for the daily demand and the standard deviation. And you can see here that there are a lot of decimal points that I don't need. So I'm going to format it to just one distribution, one decimal points. So this one is also a random function. So it gets different values when you refresh yourself. For day 2, I'm going to use the if statement and say that, okay, only generate or sample for this column if the lead time is greater than 1. That means if the lead time is actually more than 1, then we have day 2. If day 2 exists, then generate demand for it. If day 2 doesn't exist, don't generate demand for it. So this is going to be a norm again in red, the rand function, and then the mean and the standard deviation here. If day 2 does not exist, you can generate a 0, or you can just, to not have a lot of zeros here, you can just produce empty spaces here. It could be neuter. For example, right now, the lead time is 1, so day 2 and day 3 does not exist. So that's why we don't have a demand here, but we have a demand for day 1. If I refresh it here, I may get a lead time more than 2. So day 2 right now actually exists, so that's why we generate demand, sample demand. So let me format this as well. For day 3, we can actually copy this and just paste it here, except that I have to change this to 2. So I would say if day 3 for lead time exists, that means if lead time is actually more than 2, or if it exists, then sample from the normal distribution. So for example, kind of stuff. Okay, so right now the day is 2, lead time is 2, so that's we don't have actually day 3. Okay, and the total is just the summation of these day 1 and day 2. Okay, so for example, right now, the lead time is 2, so we have demand for day 1 and day 2. We don't have demand for day 2. Okay, refresh this to see if it works for day 3. Right. Okay, so you see you have the lead time is 3, so that's why we have daily demand for day 1, day 2, and day 3, and the total is just the summation of this. Here we're going to compute whether we have inventory. We have the inventory stock out or not. So the ending inventory would be how much we had in inventory when we reordered minus the demand during the lead time. So here we're going to say if this value is negative, that means we have a stock out. So print out as 1. If otherwise print out as 0, that means we don't have a stock out. Okay. So now I can actually copy this down here, and then I'm going to drag this down up to 1000. So we do the replications of 1000 replications. So you see that this is 1000. Okay. If we hadn't done the empty space here, you would see instead of this empty space here, you would see a lot of zeros. So right now I think it's it actually looks better with arms. It's less messy. Okay. So you see a lot of zeros on 1. And we need to come up actually with a summary for our simulation. So that's what I'm going to do, a summary here. For example, let's do here, summary simulation. So for example, here I want to compute the number of replications, you know what that is. And that's actually 1000. The number of stockouts, which is, I'm just going to sum up these zeros, these 1 and zeros here. So it's going to be H18 up to H1017. And then service level. So service level would be 1 minus the probability of a stackouts. So the number of stackouts divided by the number of replications. So that's 53% almost. I'm gonna go with 1 more decimals. And this is going to be, service level is going to be actually our output. So I'm going to use the output format here with style. And here I'm going to generate the 95% confidence interval. The lower and the 95% confidence interval of the values. Okay. So to do that, we need to compute the standard deviation of error, standard error. So the standard error for the service level is kind of a proportion. So if you remember from a statistic also, as you remember from last time that we had lecture, the standard error for proportion is the square root of pi multiplied by 1 minus pi divided by n. So that's what I'm going to use SQRT here. The value would be the service level, which is proportion, multiplied by 1 minus proportion, 1 minus pi, divided by the number of iterations in the n. This is going to give us the standard error. And the 95% confidence interval, lower and upper, is just going to be the service level plus minus 1.96 multiplied by the standard error. So this would be the standard error minus 1.96 multiplied by the standard error. And for the upper, it would be the service level plus 1.96 multiplied by the standard error. So if I use this format for these two, this is how they would go. So the standard level, the service level right now, when the reorder point is 50, is 54% almost for 53.9. And the 95% confidence interval is something between. So we would say that we are 95% confidence that the service level is between 51% almost to 57%. And this actually would demand on the reorder point. So for example, if I change this reorder point to 60, you see that every value is going to be generated and recomputed, and we're going to get a service level of 72.5% here. And we are 95% confidence that the service level is a value between 69.7% and 75%, 75.3%. So you see that it is actually, if I just generate new numbers, you see that these values all change, but the average between these two are kind of are in a close bracket. Okay? So it is a function of the two random variables, the lead time and daily demand, also a function of the reorder. So let's actually do a one-way table to study investigate the impact of reorder point on the service level. Okay, so let's do that here. So we're going to generate a data table here. Data table. In this data table, I'm going to do a impact of reorder point on the service level. So I'm going to call it SL here. That's SL here. So it's going to be this value. And the 95% confidence interval lower, and the 95% confidence interval up. Okay, so this is reference to this cell, and this is reference to this cell. All right. All right, so we're gonna start with the 60 here, and we're gonna go 65, and we're gonna go up to 100. Okay, so now I'm gonna select all of these. I'm gonna go to data, go to Vaadin analysis, data table, and then on column, I'm gonna say for the order point, I'm gonna reference this cell. I'm gonna hit OK, and it's gonna generate all these values here, as you can see. And I'm going to format it. This is going to be our replication. So you can see that the service level has about 72%, 73%, 78% if the reorder point is 65. As we increase the reorder point, our service level also increases. And between 75 and 80 reorder point, you see that we have an order of between almost 90%. So somewhere between 75 and 80 for reorder point, they are about 90% of service level. So you can investigate that for values between 75 and 80 to find like exactly where it is. Is it 78? Is it 79? Is it 76 or 77? Okay. So, but we kind of know that it is between these two. Okay. All right. Let's go back to our lecture. Do input distribution matters? So here we assume that the daily demand will follow a normal distribution with an average of 25 and a standard deviation of 5. And also we assume a distribution, a random discrete distribution for daily time. So the question here is, would the type of distribution matter here on the output? Well, actually, it depends on the question. It depends on the system. It may or may not, actually. So it depends mostly on the distribution's variability. The variability of distribution may actually have a large impact. So you could have two different distributions, for example, uniform distribution and normal distribution with the same standard deviation and the same average, but they have totally different shape. The uniform distribution, if you remember from statistics, has a rectangular shape, and the normal distribution has a bell shape. So although they have different shape, but when you use the same mu and average, the same average and the same standard deviation, they may not actually, the impact on your system may not be actually that different. It would look like. But for example, for another distribution that has a lot of variability, such as exponential distribution, you may get actually a lot different outputs with. So what you could do here, you could actually build up your system, run your system with using a uniform distribution of A and B. A is the minimum value, B is the maximum value. And then also do it for a normal distribution with sigma and mu, so that mu is actually A plus B divided by 2. That's the average of this distribution. And the sigma is B minus A divided by 4. So basically, you're running the same normal distribution with the same average and standard deviation. If you see the model output do not change much, then the source of randomness is not actually a big deal. It's not crucial. Otherwise, it is. So let's talk about example here to see whether the type of distribution would have an impact or not. So imagine a queue, a service queue, for example, a coffee shop that have one server. So that's called a single server waiting line. Okay, we are considering here actually a couple of different scenarios, 4 different scenarios here. The queuing model have the inter-arrival time, the service time distribution, the service time average, and the standard deviation. And the output of the system is the average number of people waiting in line, that's the length of the line, and the average waiting time that you would have to wait in the line. So the first case is when you don't have actually any randomness. That means that everything is just fixed up. For example, the inter-arrival time, every 51 seconds exactly, you would get one customer, which is like a big assumption, unrealistic assumption. And also the service time, no matter what customer wants, whether they want black coffee, whether they want latte, whether they want the tea, it's going to take exactly 50 seconds. So there's no variability here. It's deterministic. The average is 50, and the standard deviation is 0 because there is no randomness. So you would actually get no line at all. So there would be no person in the line, and the waiting line would be 0. In another case, we assume that the service time follows a uniform distribution between 15 and 85 seconds, the service time. The average service time is 50, and the standard deviation is 20.2 seconds. So for this system, which we have randomness, but it follows a uniform distribution, the output is, as we can see here, the average number of people waiting in line is 3.16, and the waiting time to wait in line is 2.68. The next case shows another system, this system that follows another distribution, which is normal distribution by the average of 50 and a standard deviation of 20 seconds. So for this also, the average is 50, similar to the uniform, and the standard deviation is 20, which is very close to the previous standard deviation for uniform distribution. So the output for this has been computed, as you can see here. The average number of people in the line is 3.21, which is close to the average people in the line for the uniform distribution. The waiting time is also very close. Okay. The last, so this is actually two different distribution, uniform and normal. They were the exactly similar, the same actually average and very similar standard deviation, and the output also are similar. So two different distribution, but similar output almost. The last case shows actually a different distribution, which is exponential distribution with average of 50. So the average is the same in all of these cases. In all of these 5 to 4 cases, the average is the same, but the standard deviation or the variability varies here. So the variability in this exponential distribution is very high, and it is 50, more than twice the others. So for this system, we get actually totally different outputs. So the average number of people waiting in line is 15.5, which is almost 5 times of the other two distribution. The waiting time is also between 5 to 6 times more than the other two distributions. So as you can see here, the average for these 4 scenarios are the same. The variability changes, And that's the variability is the one that actually has big impact, not really the shape of the distribution. So that was our, that's kind of our lecture. Let me also finish up with the last one. So you may wondering, hey, what type of distribution should you use? So the best way to go with this is just trying to estimate the distribution by the graphing the histogram if you have previous data. So use your historical data and use a histogram of your historical data to come up with if the shape of it kind of looks like a bell shape, kind of similar. It doesn't have to be a perfect bell shape. Or if it's kind of uniform, it may have up and down, but it kind of looks like a uniform. So it best maybe to be estimated by a uniform distribution. But there are actually mathematical, statistical tools and softwares to do the job perfectly for you. But we're not going to go through that at that level of statistics. So yeah, that's about chapter 10. We are done with chapter 10.